Today we are going to start a next topic, direct product and Sallow's theorems. So this is again very important topic. So first, what is the direct product? So there are two kind of direct product. One is external and second is internal. Now here in this definition, so we are discussing the external direct product. Suppose this G1, G2 and Gn, these are finite group. These are group of order finite. Then their Cartesian product, whose element are of this kind, is a group, is again group under the binary composition, this binary composition, and this group is called a external direct product of the groups G1, G2 and Gn. So this is a definition of external direct product. Now my first theorem is to prove that this external direct product is a group under this binary composition. So that was a question or theorem that is asked in GNDU 2005. So there are very simple result to prove that it is a group. Now to prove the group under this binary composition, so my first property is closure. So just understand all the properties. So first is closure, then associative, existence of identity and existence of inverse. Now if I take two element A and B belongs to G, so very carefully, then it means these elements are of this kind, A1, A2 and AN. Similarly, B are of this kind, B1, B2 and Bn, where each AI and each Bi belongs to G. So this belongs to G and Bi, this belongs to G. Now I define the binary composition in product, that is a AB. So this is a product of these two Cartesian product. So that can be written as A1 B1 comma A2 B2 comma AN BN. This is of this kind. Now this will belongs to capital G if each term, this belongs to A1 G1 and this belongs to G2 or this belongs to Gn, then this Cartesian product belongs to G. Now we know that since each AI and Bi, this belongs to Gi, so this belongs to Gi, this is a Gi. Now what is Gi? Gi is group. So group is closed under binary compositions. So this element belongs to Gi. So it means this first element belongs to G1, second belongs to G2 and this nth element belongs to Gn. So it means then entire Cartesian product belongs to G. So G is closed under the given binary composition. So that is my first result. Now second result is associative property. So second result is associative property. Now I take three element A, B and C. It belongs to G. So it implies A is of this kind, A1, A2, AN, right? And B is of this kind, B1, B2 and Bn, and C of this kind C1, C2 and Cn. This is an n-tuple where each Ai, each Bi and each Ci, all of these belongs to Gi. For every I is running from 1, 2 and so on up to n, this values. Now to prove the associative property, so this is AB Cartesian product, AB product into C. So what is AB? AB can be written as A1 B1 comma A2 B2 comma AN BN, this values. So this is the value of this AB product into what is the value of C? This is a C1, C2 and Cn. Now again multiply with binary composition. So this can be written as A1 B1 in bracket into C1. Again A2 B2 in bracket into C2 and so on AN BN in bracket into Cn. Now each AI, Bi, Ci belongs to Gi. And what is Gi? Gi is a group. So if it is a group, so it holds associative property. If it holds associative property, so this member can be written as A1 into B1 C1. Why this is possible? Because Gi is a, G1 is a group. Similarly, G2 is a group. So this value is, similarly An into Bn Cn, right? Now split it. So this can be written as A1 comma A2 so on An, and this value is equal to this product B1 C1 B2 C2 and so on. So this is equal to, this value is B1 C1 comma B2 C2 and so on Bn Cn. Now this value can be written as A, and what is this product? This is a B into C. For every A, B and C belongs to capital G. So it holds the associative property. So second result. Now third result is existence of identity. Now what is the existence of identity? For every A belongs to G. For every A belongs to G, so we want to find out the element of the kind identity in the G. So for every A belongs to G, so where A is equal to A1, A2 and so on An, and this AI belongs to Gi, these values. Now there exist clearly, we can find the E element, which is a E1, E2 and so on up to En. So what is this? It is an identity of G1, identity of G2, identity of En. So what is where Ei, what is this? It is a identity of Gi. It is the identity of Gi. Now to prove it is act as identity of this group G, so A into E, these values. So this can be written as A1, A2, comma An into E1, comma E2 and En. So what it means? it means this is AE1, AE2 and AEN, this values. Now this value is equal to A1, this value is A2, this is AN. Now since A1 is a member of G1 and E1 is identity, so it acts as A1, A2, comma so on up to AN. So what it means? It means this is equal to A. Now similarly, we can write it as EA. So what is E? E is E1, E2 and so on up to En into A1, A2 and so on up to An. So what it means? It means this is a E1, A1, E2, A2 and so on up to En, An. Again this is equal to A1, A2 and so on up to An. So what its value? Its value is equal to A. Now what we get? We get AE, this values, AE which is equal to EA and this value is equal to A. So it means E is identity of G. So it proves E act as identity of G. Now next step, which is a fourth, which is called existence of inverse. So what is next? So this is a existence of inverse. Now here we will prove the existence of inverse. So for every A belongs to G, again this is of this kind, A into A1, A2 and AN, this values, or AI belongs to G, this members. Now to find the A inverse, we write A inverse as this value which is equal to, now it is a A1 inverse. Why it is possible? Because AI belongs to G, G is a group and group has inverse. Similarly, we can find A2 inverse. Similarly, AN inverse. Why it is possible? Since this G is group, so it means AI inverse exists and it belongs to G. So we get A inverse of this kind. Now what is A into A inverse? This values. So first write A into A inverse. This can be written as A1 inverse, A2 inverse and so on, this product AN inverse, this values. What is this? It is a identity E2 and En. So what is this? It is a E dash. So identity of G. So I write it as E. If I write it as E, so it is identity, not E dash. So it is a E which is equal to E1, E2, En. Similarly, A inverse into A. So this product will become A1 inverse into A1 and A2 inverse into A2 and AN inverse into AN. So this value, again this value is equal to E1, E2 and En. So this is equal to E. So what we get? We find A inverse, which implies A into A inverse, which is equal to A inverse into A, which is equal to identity. So it proves that all the property of group. So it means this G is a group. So we prove that this G, which is a external direct product of this values, so it is called a group, right? Now here remember that if all the GIs are abelian, then G is abelian, number one. Number two, so here remember two result. If all GI are abelian, so if G1, G2 and so on up to Gn, if they are abelian, so we can easily prove that their direct sum G is also abelian. This is also abelian. Now if binary composition is in addition, so this is a external direct sum. So in that case G can be written as G1 plus G2 and plus Gn, these values. So this can be written as here. Now A is, if I take A belongs to G, so this is of the kind A1 comma A2 and comma A3. So here the binary composition is, if I take A and B belongs to G, now binary composition is sum. So sum is A plus B, which can be written as A1 plus B1 comma A2 plus B2 comma An plus Bn. So here binary composition is plus. So if it is a binary composition plus, so it is a external direct sum. If a binary composition is product multiplication, then it is called a external direct product. Now next theorem is theorem related to internal direct product. So first understand the definitions. Statement: let G1, G2 and Gn be a finite group and let this is a direct product. This is a Cartesian या external direct product. Now EI is identity of GI, as we know that. Then for every HI, if I define HI of this kind, all tuples are identity except ith has some non-identity element, some element AI belongs to GI. Now to prove that it is a normal subgroup, number one. Number two, it is isomorphic to GI. So it has two property. One is normal subgroup and second is it is a isomorphic to GI. And third, second property, HI and HJ, it does not commute to each other. It means if I take one element from HI and second element from HJ and they are distinct, they does not commute to each other. It means it does not hold the commutative property. And third is, for every A belongs to G, it is uniquely expressible as product of A1, A2 dash and An dash, where Ai dash belongs to Hi, right? Where Ai belongs to Hi, so it means G can be written as the product of H1, H2 and Hn. So this is a definition of, this is a theorem as well as definition of the internal direct product. If binary composition is multiplication, if binary composition is addition, then it will become the direct sum. Now we will prove this theorem step by step. So first, the given part hi. So what is a hi for every hi? So this set consisting element E1, E2 and ith term is ai and last en such that this ai belongs to gi, where gi is the group of G. Now, to prove that it is a subgroup, number 1, number 2 normal subgroup, and number 3 it is a isomorphic to gi. So it has 3 property. So to prove it is a subgroup, so prove first it is a non-identity. So since we know that this ei at this place belongs to gi, so it implies clearly E1, E2 and so on up to En. So this element belongs to hi. It implies very carefully hi is a non-identity. If it is a non-identity, then we can choose any element. If it is a non-empty, so we can choose any element from this set, because if it is an empty set, then we cannot choose any element from this set. So first step, it should be non-empty. Now I take two elements. First I take ai dash. So what is the structure of ai dash? Very carefully. So this is a E1, E2 and so on up to ai and next En, and this element belongs to hi, where this ai is element belongs to gi. Now I take bi element, bi dash. So again this is in same as E1, E2 identity. So here I will take bi and so on En, and again it belongs to hi. So it means this bi belongs to gi, this values. Now to prove the subgroup, I will prove that ai dash into bi dash inverse belongs to hi. It belongs to hi. It belongs to, so here I write it as hi. Now this value is, so here if I write it hi, so here correct it as hi. Now ai dash into bi dash inverse. So this is a ai. Here it is E1, E2, ith element ai, last element En, and what is its inverse? So identity inverse, it will be E1, it inverse, it will be E2, but it inverse will become bi inverse, and next En term inverse is En. Now taking the product, so E1, E2 and so on ai, bi inverse, so on up to En, right? Now this element belongs to hi. So why? So why this element belongs to hi? So just check the structure of hi. In the structure of hi, the ith element should belongs to gi and other are identity of each group. Now since we know that ai and bi, these are element of gi, right? So what is gi? Gi is a subgroup, ja group. So if it is a subgroup, ja group, So it means it implies AI BI inverse belongs to GI. So it means this element belongs to GI. It is identity of G1, G2, and this element belongs to GI. That's why this belongs to HI. So it means this HI basically it is a subgroup of subgroup of a group. This is equal to G, right? So it is my first step to prove it is a subgroup. Now second is to prove it is a normal subgroup. Now I take one element from HI and one element from GI. So to prove it is a subgroup of this G, so I take X is equal to of this element X1, X2, Xi and so on up to Xn. This element belongs to G. Now what it means? It means each Xi belongs to Gi, because G is the Cartesian, the direct product of G1, G2 and so on up to Gn. Now to prove it normal, I take X inverse and second element from HI. So I take AI dash. So here it is Xi. So I take, substitute its value. So its value is X1 inverse, X2 inverse and so on, Xi inverse and Xn inverse. Now the second tuple is AI dash, which is E1, E2 and here AI and so on En, where AI belongs to, and third product is X, so which is X1, X2 and Xi, and last it is a Xn, this values and this values this. Now taking the product, so what is its product? X1 inverse into E1 into X1 inverse, and similarly second term, and ith term is goes to ith term Xi inverse, this values, into AI into Xi and so on up to Xn inverse En into Xn. So since it is identity, it act as a product of Xi inverse, X1 inverse into X1, so it will become a identity E1. Similarly at ith place it is a Xi inverse AI into Xi and so on. This is again identity which is a En. So we get these values. Now since Xi belongs to Gi, also we know that AI belongs to Gi. Gi is a group, so it implies it inverse is also belongs to Gi. So all the three element belongs to Gi, then their product, because it is closed under binary composition, Xi inverse into AI into Xi, it belongs to Gi. So it means this element belongs to Gi. If this element belongs to Gi, then this product belongs to Hi. What we get? We get Hi satisfy the property of the normal. It means this Hi is a normal. This Hi is a normal subgroup. Normal subgroup of group G, normal subgroup of group G. It means it satisfies the property number 1. It is a normal subgroup. Now second is, it is isomorphic to GI. Now to prove the isomorphic, let I take a sum mapping Fi, which is from GI to HI. Now we know that the element of HI and GI. So what are that element? This is defined by f of AI. This is Fi, which is equal to, even I can use it is as this is for every I can also use here it may be write it as J. So this is equal to E1, E2 and so on up to here it is a AI and this value is equal to En. This is for every AI belongs to GI. AI belongs to GI. Now this mapping, my aim is to prove that this GI is isomorphic to HI. So each GI is isomorphic to HI. Here I can also take not as a Fi, I can simple take it as phi mapping. So don't take it as this mapping. So not phi I take the simple phi mapping. Now if I take the phi mapping, now to prove it is isomorphic, so first it should be well defined, and second it should be well defined homomorphism 1 1 as well as onto. So I take two element AI and BI, it belongs to GI, as we know that. So what is a phi of AI into BI? So by definition this can be written in this way. So this is E1, E2 so on here at this place AIBI. Why? Because of this element. So comma and so on up to En. Now split as a product of two n tuples. So if we split as a product, this will become E1, E2 and here AI so on En, and this value is again E1, E2, here it is BI, this values, and this is a En. So this value is equal to phi of AI, this element, into phi of BI, this values. So what we get? We get phi is a homomorphism. So this is my first step, this mapping phi from GI to HI. So clearly this map is a homomorphism. After that, to prove it is a 1 1. So there are two ways to prove it is 1 1. One is its kernel consisting identity element, or second is it is a f phi of AI is equal to phi of BI. Then prove that these two elements are AI equal to BI are equal. Now I prove its kernel consisting identity element. So I take some element which is from GI. So this is of this kind AI. So I take it is belongs to kernel of phi. So what is the definition of kernel of phi? So its image should be identity. So what is the identity of? So this is E1, E2, EI and so on En. Now substitute the value of phi of ai. So what its value? So just substitute E1, E2 and so on up to ai. This is up to En, which is equal to E1, E2 and so on up to Ei, and this is En. When both are equal, then their corresponding entries are also equal. So this will be equal to this values, this will be equal to this values, and this will be equal to this values. So it implies ai becomes a identity. So I take this element from this, and this elements act as identity. It means kernel of phi consisting only identity elements. So which is only identity elements. So it means this phi is 1 1. This phi is 1 1. And clearly it is onto, because every element from the right hand side there exists a element. So clearly it is onto. How we can prove that? For every element E1, E2, ai and this is En belongs to hi. What it means? It means there exists ai belongs to gi, as we know that, such that phi of ai is equal to E1, E2 and so on ai and En, this values. So this value has pre-image. If this value has pre-image, then phi is onto mapping. So phi is homomorphism 1 1 as well as onto. So what we get this gi is isomorphic to hi. This is for every I. This is for every I. So each gi is isomorphic to hi. So it means they act as a hi. So they have the same structure. If they are isomorphic, it means they have different element but same property. So it means the isomorphism. Now second, it is a first step. Now second is कि it commute hi and hj, it does not commute to each other. So that is the second property. So let I is not equal to j. Now I take ai dash, one element. So what is one element? So this element can be written as E1, E2, continue, here I get ai, so on, this value is En. So this belongs to hi. This belongs to hi. Now second is bj dash. So what is this? This is a E1, E2, so on, here ei and so on, here bj. So here it will be ej and so on up to En, and this belongs to hj, this values. So it belongs to hj. So I take this ai, aj and this values. So what we get? We want to show that when I is not equal to j, then it commute to each other. Not does not, it commute to each other. hi is equal to hj and hj is equal to hi. So here ai dash into bj dash, which is equal to taking the product. So this will become E1, E2 and so on ai so on ej en. Similarly, second number, which is e1 e2, so this is so on up to ei, then bj, continue bj and en. So what we get? We get this product e1 comma e2, then it will be ai, and so on. Here it will be bj and so on up to en, these values. And similarly, now bj dash and ai dash. So what is bj dash ai dash? So this will become a of this kind. So here bj, which is e1 e2, here it is ei and so on bg, these values, so on up to en. Now from this it is a e1 e2, here it is ai and here it is ej and so on up to this values en. Now again we multiply, so we get here e1 e2, then after some term I get ai term, then goes to next I get bj term, then goes to next en term. Now both these are equal, that it implies ai dash bj dash, which is equal to bj dash into ai dash for every I not equal to j. It means hi and hj, they are equal to hj into hi, this product. So here remember these values. So this is, now after that we know that the third part, that is G can be written as the product of each H1, H2 and Hn, then prove it as uniqueness. Now third part, consider some H, some A belongs to G, these values. Then what it means? It means this A can be written as A1, A2, so on, AI, so on, AN, where each AI belongs to G, because it is a external direct product of these values. Now this A can be written as A1, comma, E2, so on up to En. This value is first term. Second term I am writing E1, A2 and so on up to En. So similarly third term and goes to nth term E1, E2 and so on up to En. Now check that this element is A1 dash and it belongs to H1, and this is a A2 dash, it belongs to H2, so on AN dash, where each AI dash belongs to HI, right? So element of G can be written as the product of HI. Now next is this expression is a unique. Now to prove it is a unique, we take some another expression, that is suppose I take the second expression, which is a B1 dash, B2 dash and Bn dash, these values, where Bi dash belongs to Hi. Now both are equal. If both are equal, so this can be written as A1 dash A2 dash AN dash, which is equal to B1 dash B2 dash and Bn dash. Clear? Now substitute its value and taking product, what it becomes? So it becomes a A1 comma A2 so on AN. So just substitute the value of this and this, then multiply. This value will become A1 dash A2 and similarly it products. So this will become B1 B2 and so on up to Bn in n tuples. Now if the n tuple are equal, then corresponding entries are equal. So it means Ai is equal to Bi for every I. It implies if they are equal, then Ai dash is equal to Bi dash. So which prove the uniqueness. Now from next is definition of internal direct product. A group G is called an internal direct product of its subgroup. So all of these are subgroup if it satisfies two conditions. Condition number 1, any two distinct subgroup commute to each other. This means Hi is equal to Hj and Hj is equal to Hi, and each x belongs to G can uniquely expressible as its product x1, x2 and xn, where xi belongs to Hi. So it means it is a internal direct product of the our subgroup. So what it means? It means H1, H2 and so on Hn. We can write it as a in this way. Second is Hi, Hj is equal to Hj, Hi for every I is not equal to j. So this is called a property of internal direct product. In case of if the binary composition is addition, in that case it is called a direct sum. Here it is product. If the binary composition is plus addition, in that case it is called a direct sum. So direct sum. So direct product can be written as G H1 this multiplication H2 and so on. This is a direct product, and direct sum can be written as this plus H1 this plus H2 and so on plus Hn. So what it means? It has two properties. One is G, element of G can be written as element of H1, H2 and Hn. Number 2, it commute with any two distinct subgroup commute to each other. Next